Hello everyone, welcome to this keynote presentation for the student and young professional activities of IECON 2020. My name is Samir Koro and I will be presenting you today about energy transition and why this is not just a need but also a opportunity. So thank you for taking some time to see this webinar, this web-based version of the presentation that should have been done at the conference. But in looks of what we have had with the global pandemic, this is the best way to reach out to you. So a little bit about the table of contents of this presentation. I will talk a little bit about climate change and how this is forcing an energy transition, and then see some of the challenges and opportunities that this transition is imposing us. And I will finish with some examples of things that we have been doing here at my university to maybe motivate you to do something on your, also in this area in your university or in your company or wherever you are working. So because you are a young professional or student, you have more than 30 years of career ahead of you. So this is really important. I believe I could do this presentation to you, so maybe it could provide you some insights on where the big issues are, and so you can make some more informed and decisions, or maybe think about the decisions that you are making. So we are in the midst of this great environmental crisis, probably one of the biggest crises of modern human history, which is due to the increase of temperature, in the average temperature in the Earth. And the same thing as when you have some fever and you feel differently, this extra degrees on a global scale are also making the Earth behave differently and is sparking some climate change in some areas and regions around the world. And you can see this manifested in terms of droughts and wildfires and big storms and the melting of the polar caps and so on. So it is a big issue. It's threatening our quality of life. It's threatening the sustainability of life itself on Earth. And this is, of course, a big issue. We know which is the cause of this problem, and we know it's because of greenhouse gas emissions that are preventing the natural cooling of the Earth. And the origin of this greenhouse gases is mostly of the energy sector. As you can see here in this pie chart, more than 70% comes directly from the energy sector, while only 25% comes from agriculture, forestry, and other uses of the soil. So this is a problem, and it's an energy problem, and therefore there is where the solution is at. So this is forcing an energy transition. We have to move away from fossil fuels that are the ones that cause the greenhouse gas emissions for the most part. And in addition to that, we know that there are other issues related to fossil fuels, which is that they are a limited reserve worldwide. So therefore, their price go up in time because it's a limited resource. And it's also not available evenly or distributed across the world. And this causes other issues like it reduces the development in some continents like Africa and South America that have lower penetration of fossil fuels, lower availability, I would say, in resources on fossil fuels. And because it's a fossil fuel based economy in the world, that's why these continents are lagging in terms of development, right? So that generates also inequalities and other issues, not just the climate change. So anyway, both things, but particularly climate change, is forcing a energy transition. But we have known these things for more than 30 years, actually. When I was a kid, I already could hear in my school's talks about climate change and how this would be important in the future. But it seems that just in the last years, this has turned up a notch a little and has become more urgent than ever. And why is this? And as you see this picture over here, you probably recognize this movement that started last year regarding climate change, which Greta Thunberg was a little bit the face of this movement. But although she was the face of the movement, it was millions of people around the world that really feel that this is an urgent topic. And the reason for that is that this is the first generations of humans that are really going to experiment all the consequences of climate change. So this will affect the quality of life, particularly of the people that are now very young, in their teens or in their 20 years and so on. So they will for sure experience climate change more than people that are 40 and up, right? So that's what's making this urgent. And this group of people is increasing year by year, of course, and they're now getting into the voting booth, and that of course has made politicians aware. And also they are the ones buying the goods, so this has also made the companies aware. And this is why there's now political, economical, and social reasons for why this is urgent. This is not our first energy transition. We actually, when we discovered the ways to control and produce fire, we moved from being, that's what set us apart from animals, right? That's where we really became humans. So this was our first energy transition, and this is what actually made us human. So you can see across the history how all the energy transitions have actually molded the way humanity has evolved, exploration and then industrialization and so forth has been by the hand of energy transitions. And as you can see, the last one, the one I'm talking about now, is maybe the only difference that it has is that now it's not about improving quality of life or productivity. It's based, or now the goal is because of sustainability. It's to make life on Earth sustainable for the long term. But one underlying equality, or something that's common to all these energy transitions, is that they have been possible thanks to technological development. Each one of them has been made possible by breakthrough in technologies, maybe the ones in the beginning more by empirical evidence and trial and error and inventions, if you will, and now more based on scientific experimentation, the research and development and innovation, and they are more intensive in the terms of knowledge than the first ones, right? So, but as one would say, okay, just develop this technology, right, and we're good. But if we look into science fiction as a reference to see how difficult it is to improve energy related technology, you will see something very interesting, a trend that it's kind of remarkable. If we see, for example, in transport and space exploration, science fiction has predicted spaceships and stuff like that, and we have actually accomplished a great deal of it. And when you see robotics and you see these assistance robots, and you see that we have now robots that can bring you food, it's something that's kind of actually there in the same realm. Of course, it's not the same, but it's kind of close. Also, bending phones and holograms and stuff like that, that we have actually taken from the inspiration from science fiction, and that have become reality. If we look into the energy area, it's a kind of opposite. If you see stuff like lightsabers that are powered, by the surrounding energy or the force or whatever spiritual thing it is, or fusion that can fit into a vehicle, or harvesting energy from humans and stuff like that. These are things that are really far-fetched, and there are more fiction than science. So this makes you wonder why even science fiction has been struggling to come up with some futuristic ideas on how to produce clean energy. Makes you wonder if there's something underneath that, if there's something strong that makes that difficulty patent. And I've thought about this, and these are the four things I come up with to analyze why it has been so difficult to develop energy technology. And one of them is that energy is a very difficult concept in physics. It's not like, oh, a meter, a kilogram, or stuff that you can actually measure and feel. And where the concept is more is less abstract. So energy, depending on the physics course you have, so energy is heat, it's a wave, it's light, or it's a state of matter, or even if you go into more relativity, the parts of physics, they say matter is equal to energy. So it is a concept that for the general people is more difficult to grasp, it's more abstract. And then of course we have that fossil fuels have been a cheap and apparently never-ending source of energy. That's for the last 200 years has been so, or 150 years has been so. So energy wasn't a real problem. So why thinking about it? Why actually trying to improve on it? If it's not broken, don't fix it, right? So, but it has come apparent now in the last decades that it is a problem. And then we have, of course, started having some political and economical pressure because it was already a fossil fuel-based economy. So moving away from that, there was a lot of inertia. The markets are built this way, you know, jobs, employments, industry, and so forth. So it was difficult to move away from these models and these economic models because they were already put in place. And just because of the initiation of this environmental sustainability movement that started in the 70s, have we become a little bit more aware. And this is basically thanks to the Apollo program, because this is the first time we could see the Earth from outside and see how small it is against the backdrop of the universe and how fragile it is. And since then, we have caught up with a little bit the sustainability concept and environmentalism movements that have brought this into our attention. So that's why it's something so recent, and this is why I believe it's something that has been so difficult. And that's makes me to be, I mean, I am optimistic. I'm a professor that works in R&D, so I always look at the glass half full, but it makes me look at this with some caution in the way of how big and fast we can make this change, because how difficult this is and apparently is, right? So this sparks a question here for you, and you are a young professional, you're a student, you have at least 30 years of career ahead of you, and of course there is job and things to do in places where you can, there's development to do, and therefore my question for you is, where are you going to focus your career on related to this issue? So we have a huge problem here with a lot of areas of development. So you have actually some planning to do, some strategic decisions to make. Are you going to work on batteries? Are you going to work on microgrids? Are you going to work on electric vehicles? So of course, all of these things are very interesting, but some of them are more underway. Some of them are a little bit lagging. So this is a little bit the topic of this presentation, to show you some of these things and where you can actually make some interesting career decisions. So we have to actually move away from a city like the one you see in this picture, illustrated in this picture over here. We wanted to move to a more sustainable structure like the one you see here at the right. And I'm going to analyze all of these in the upcoming slides to give some examples of these. Okay, so for example, in power generation, of course, we have to move to more renewable energy sources, wind, solar. That's of course under really something that's coming bigger and bigger right now. Also, we have energy transmission. So in transmissions, these energy sources are not usually close to the consumption areas. So you have to transport this energy, and that's also done with industrial electronics technology, HVAC, HVDC. Transmission lines. Here you can see also offshore power plants that need their substation to transmit power to the shores. If we look also into some areas of consumption of energy, electric buses, also a LED lighting, not just on the roads, but also in buildings, inside, outside, and so forth. And production of hydrogen that could be done from renewable energy sources. That's also a way of storage of energy, also very important. And for example, if we look at this side, we can talk also about distributed generation microgrids, not having all the generation far away from consumption areas, but you can have them on the rooftops of companies and buildings such as stadiums and shopping malls and so forth. Also, more integrated microgrids where you have generation, storage, and also consumption, like in electric vehicles, in which the power flows can go and back and forth to optimize the system. So these are all technologies that are in the realm of having a more cleaner and more sustainable world. Also electromobility, EV technology. Here we have, of course, electric vehicles and everything related to their powertrain, the batteries, the electric machine, motors, and so forth, energy management systems. Also the charging infrastructure, fast charging stations like this one with DC fast charging, or also opportunity charging stations in the cities and supermarkets and cinemas and so forth, and shopping malls in which you have DC charging or AC fast charging. So all these are areas that are important for energy transition. But what I would like to show you here is where we are at. So this is a chart made by the World Economic Forum, five different sectors: so power, energy integration, transport, buildings, and industry. And here you can see in the middle with dark blue are the ones that are not on track, not even close to being on track to go to a more sustainable solution. Then in the middle we have areas that need more effort, that they have something has been done, but they are not fully there yet. And then the ones that are right on track. What's really problematic from some point of view, that you can see that there are very few on track. Okay, that's a bad thing for energy transition. It is a good thing in job opportunities and career development, of course. So you can see that solar PV is on track. It's actually quite mature technology. You can buy PV modules, inverters, and so on. It's on good track. Electric vehicles, as we will see later and discuss later as well. LED lighting, of course, too. But you can see in the area of industry, everything is not on track, is lagging behind. Chemical, cement, mining industry, etc. These are really high carbon footprint industries that where you need to do that need things need to change. In transport, we are good in electric vehicles. I would even push electric buses here on top as well, and trains. But what's really lagging is actually aviation and also shipping, international shipping. The ship industry. I would not put the ship industry in the in more effort needed. I would put that on not on track whatsoever. Also in buildings, we have the heating the heating part that's not, and cooling that are lagging, and just lighting is advanced. So as you can see, there are a lot of fields and a lot of areas in which industrial electronics is really important, but where we are lagging behind. So since you have a 30-year, I know it's very sometimes tempting to go for the low-hanging fruit, the things that are right there right now, like electric vehicles, solar, and so on. But you really have to think about this as you have 30 or 40 years of career ahead of you. So maybe make a step into the outside of the comfort zone and tackle maybe one of these broader, more difficult topics. That could be maybe a solution. So I will focus my presentation moving forward on power and energy integration as for one part, also transport, and also industry. I will leave buildings out for this webinar because this is not my field of expertise. So I will tackle these other areas first. Okay, so in relation to power system and energy integration, we have some solutions that are already in place, in some places more than others, but of course, to increase the availability or the opportunity to integrate variable renewables like solar and wind, you need some kind of backup for when the sun is not shining or the wind is not blowing. So you basically use existing thermal and hydropower plants to have this backup. The hydropower plant is of course a better option because it has no CO2 emissions, and the other thing, it has better power regulation capabilities. So hydropower would be the way to go. Unfortunately, it's not everywhere available, and that's one of the issues. So that's a challenge right there. The other way is interconnecting systems. So by interconnecting systems, you can get to backup of other areas of a region, or even if you have variable renewables, you can have, for example, when you don't have wind in one place, maybe you have wind in another place, or solar in another place. So that's a way you can regulate the power in the system. So system interconnection is of course something very useful to increase renewables as well. And of course, the holy grail, the long-term solution would be to have utility scale storage. In this way, if you have storage paired to variable renewables, you could solve that issue. But of course, utility scale storage has the problem right now that it adds a lot of cost to the levelized cost of energy for those renewables. So solar would be more expensive if you pair it with some kind of storage, and the same as wind. The two most cost-effective solutions that we know of so far is hydropumped storage, so to store energy as potential energy to elevate water, and then use that water it's like your hydro plants, but man-made, right? And then the other one would be with concentrated solar power. So we melt salt, we store the thermal energy, and then we use that to boil water and generate steam and generate electricity, much in a similar way as a coal or a gas plant, right? But all these solutions over here, in some way or another, add cost to the system. So anything that reduces cost, that makes these technologies more available, would of course enable the possibility to integrate more variable renewables to the system. I will talk a little bit about the system interconnection. So here you can see a map of interconnecting the whole world. It might seem like something a little bit far-fetched, but maybe that's because you're looking at the world as a flat map. The distances between this point and this point are actually way shorter than they appear here. Many of these interconnections are already existing. So America is very well interconnected. Europe is very well interconnected. The same here in this part of Asia. And some big links are missing. So it's not that far-fetched. And as an example, let's take the example of Latin America. Chile has a lot of solar power. Brazil has a lot of hydropower. So if we connect Chile with Brazil, you can have a very good mix in a way to increase the penetration of solar energy into the matrix. It could also make energy more cost effective in Latin American region, and therefore also reduce the dependency on fossil fuels. If you still believe this is a little bit too crazy an idea, the first transatlantic communication cable was put in place in 1956. The first fiber optic cable was in 1988. So that's not very long time ago. And now you can see that there are more than 420 submarine cables around the world. Of course, you will say it's not the same a fiber optic cable than an HVDC transmission line. But it is not so far out there. It's not that really impossible. In fact, take a look at this. I urge you to see this initiative, gateco.org, which is a global energy interconnection and development cooperation organization. This is a Chinese initiative in which they have laid out how this would be possible, which kind of connections were. Even they have done a complete cost assessment and technical assessment and studies on how this could be done. And in fact, it is something that for looking in the longer term from here to 2050, it's something that actually could happen. And of course, HVDC and HVAC has a lot of industrial electronics in it. And therefore, this is, of course, a good area of development for you. Of course, transport, we saw earlier, it's 14% of the emissions of greenhouse gases. So moving all forms of transportation to electricity, and particularly if that electricity is generated from renewables, is of course the way to go. I will talk, some of these are more mature than others. So industrial electromobility is kind of lagging. Aviation is of course lagging. I would say that buses and trains and electric vehicles are the ones that are more advanced. I will talk a little bit about the electric vehicle issue. So it is growing at a rate of 40% annually in the last year. So it's exponentially growing. We have more than 7 million cars currently in the market. That's accounts for 1% of the total stock, right? So but still small. So there are some barriers to this, and this is at the left side. You can see some of the barriers, and one of the original barriers was that the cost of electric vehicles is too high, but this is actually being solved for the next 2 or 3 years, in which it is supposed the drop of cost of batteries really going to make electric vehicles completely even so reach parity with normal and traditional vehicles, at least in in Asian, American, and European markets. That's a good news. So that is a barrier that's kind of in the way of being solved. Range is also one of the regional concerns, and here you can see a map of different kinds of vehicles and the range they have. So we have an average of over 320 kilometers as of 2020. So this is also something that's going to be solved in the next few years. Batteries are also getting better and cheaper, so we expect vehicles to include and pack more range in the future. So this is something that's coming for sure. Then maintenance is actually something that's not really a barrier. It's actually something in which the electric vehicles excel, because the cost of maintenance is lower, and also the energy that you need to move from point A to point B is cheaper than fossil fuel. So and now we're adding the fact that batteries are improving their warranty time up to 8 years in average. So that's even larger than the average span that normal people have a car. So this is also an issue that's going to be solved or solved already. Here you can see actually the cost of ownership breaks even after 3 years for the current scenario, and this is because the cost of electric vehicles are a little bit higher. This is comparing the same Volkswagen in fossil, combustion engine based or electrical motor based. So they cost slightly different, and then you break even thanks of the maintenance costs. And so if these two things become equal in the following years, then owning an electric vehicle will be cheaper. So that would be also something that's going to be solved in the following years. And then we have standards and regulations. As you can see, this is still a barrier. We have a lot of standards, different continents, different countries that push different voltage levels and power levels. Also, even some different kinds of protocols of communication between the electric vehicle and the charging station. And of course, the different connectors for AC and DC. So this is an issue in which still is a lot of work need to be done in terms of integrating standards into to a single one, right? Another area that is really a big barrier, and this is where we're entering the more problematic issues, is, for example, charging infrastructure. So we have 7 million cars and 6.5 million private slow chargers. So this is charging at home, basically. And then we have, but when you look at publicly accessible chargers, we have only 600,000, and 50% of them are in China. But this is slow charging, so this is not really the issue. The real issue is this one, where we have slightly above 250,000 of publicly accessible fast chargers, and you can see that more than 75% are in China. So this is something that's not solved worldwide. You can see that the other countries are US, UK, Germany, and France, and then the rest of the world only accounts for 5% of this very small number already. So charging infrastructure is definitely one of the big issues. So if you want to devote maybe your career to next following years to developing technology in some area, charging infrastructure looks like something to be where you can do some stuff in. And charging time, that's also related to charging infrastructure, because if you see DC fast charging, which is the fastest way to charge vehicles currently, the standard is around 100 kilowatts, 150 kilowatts. There are new chargers around 300 kilowatts, but still we get charging times from 20 to 30 minutes, which is not competitive to a normal combustion engine vehicle. So this is also an issue, and this has a complete direct relation with this charging infrastructure. And cultural change. Of course, this is something a little bit outside of the field of electrical and electronic engineering, but still this is, of course, a barrier for the adoption of electric vehicles. As you know, you can recognize some of these barriers. Some of them are related to the charging infrastructure. For example, range anxiety, that's completely related to people confused on how really the autonomy of the vehicles are right now. And because they don't see the charging infrastructure on the street, and that's why this leads to range anxiety. So there are some of the things here that indirectly are solved by pushing forward technologies in other departments. So what about aviation? So aviation is, of course, one of the really big issues. We cannot, this is of course a Photoshop picture. It's basically to show you that we cannot trust on economies of scale related to fossil fuel technology. We cannot just keep on improving the efficiency and improving the business model and operation of the air transportation sector. And this is something that really needs to be tackled. This is something where we're really lagging. Of course, you could talk about biofuels and made from crops, from alcohols, derived from alcohols and so forth. But those, when they combustion, they also generate CO2. So, and electric aircraft is actually more difficult because the storage issue. So yeah, you can also make the case of hydrogen. That could be it, but to get approval on having hydrogen on airplanes, that will take some time. So it's a very dim scenario for the future of aviation. If you ask me, in terms of what I mean, this will be one of the big issues on to tackle in the next year. In terms of industry, so we talked a little bit about power system and renewable integration. We also talked a little bit of transportation. In terms of industry, you can see that there is a big push from several sectors of industry on reducing the carbon footprint. This is mainly pushed forward by stakeholders in the company. And here you can see an example of Volkswagen, on how Volkswagen is actually pressuring Chile, which is one of the major producer of lithium, that is one of the components in batteries, to have a more sustainable production of lithium. So you can see that it's not just the electric vehicle, and it's even the components that make an electric vehicle, the copper that goes into the motors, and all the other things that also generate a carbon footprint. So even in that aspect, industry is now taking part of. And this, of course, gives a great opportunity. So there is an opportunity of moving whole industries that are in places where you are basically based on a fossil fuel economy. You could move those production to places where you have cheap and more clean energy. So countries that are usually not in this map that I showed you early in the beginning, that have cheap energy in terms of fossil fuels, but there are countries that have cheap energy in terms of solar and wind power, which is the case of my country in Chile. We have a lot of solar, and we are a very small economy, so we don't use all the solar that we could use. And so we can increase the demand, we can bring carbon intensive processes of industrial processes to Chile. The same can be done in Australia and other places in the world. So you can move production to places where you could have a lower carbon footprint. And then you can do stuff like metal electrorefining in those areas. So refined copper, refined aluminum in places where you have a lot of solar energy or wind energy. Currently, they're actually being refined in places where you are using fossil fuels. So this is actually another way to store energy, if you like. You can, if you cannot produce the energy to upload it to the grid, you can be using the energy to produce goods and export those goods. So this is a way of indirectly storing energy and exporting energy. Another way is to produce and export hydrogen. I'm talking about green hydrogen. Of course, we have gray and blue hydrogen, which used fossil fuels. So this is completely carbon-less production of hydrogen. And this is a very good way in which you can see how you can store solar energy and how you can transport actually solar energy in an efficient way, in a cost-effective way. So there's a lot of countries looking into green hydrogen production. As you know, this is also a thing done with this is an electrolysis process, the same as metal refining. So this is done with DC-DC converters, and if you do it with solar energy, it's also with the integration of solar energy. So that's a big opportunity there. Data centers, to put the data centers in the deserts of the world and in areas where you have a lot of renewables. So that's also a way of exporting energy. You instead of doing a big HVDC line to move the power to the place where you have the data center. You put the data center in the place where you have the power, and then you build only the data line, the fiber optics, which is way cheaper than HVDC transmission line. So you swap the idea of, instead of moving the power, you move the data, and you put the data centers in the places where you have the power. And of course, water treatment. So disinfection, desalination of water is something. Water is a big issue as well, not in terms of climate change, of course, but in terms of sustainability of the world, and also in many processes use water for industrial processes. And then, of course, you can use clean energy to produce water in places where you have a lot of wind and solar power. So what are we doing here at my university in Chile? This is a picture of the main campus in front of the Pacific Ocean. It's in the middle of Chile. And I work in two research centers of excellence in my country. One is the Advanced Center of Electrical and Electronic Engineering, and the other one is Solar Energy Research Centers. In both centers, I work with students and postdocs in developing new clean energy transition technologies that are capable of solving some of these issues that I've just shown. So a bit of context, I already mentioned that solar energy is quite big here in my country, and here you can see why. This is a map of the solar irradiance around the world, and you can see that basically Chile and some part of Peru and Bolivia have their special color. They have their own level of irradiance, which is actually the double that what you have in the south of Spain or the south of Italy, which are the premier sites in Europe. So we have actually the double of the availability of solar energy in this area, in the desert. And because of this, here you can see some examples of PV plants in the desert in Chile. These are really big mega plants, some of them over 250 megawatts. So these are really seriously big PV plants. And none of these existed before 2011. So the one here at the top left is the first one that was put in place in 2011. And so we had zero installed capacity before this one. Or there were a couple of very small ones, to be honest, but on basically non-existent in terms of statistical data. And so this one was the first one in 2011, and by now we have more than 2 gigawatt of installed capacity in the country, which accounts for 10% of the total capacity of the power system. And Chile has also a lot of mining resources and copper mines, and we do a lot of copper electrorefining in Chile. And basically you use power from the grid for the electrolysis process. You use a rectifier to produce DC currents in low voltage to go through the anodes and cathodes of copper. And so if you would like to make copper more green, reduce the carbon footprint, and you would do something like this. You would have your PV plant, and you would have an inverter connected to the grid, and then you have the rectifier and the transformer, the rectifier, and then you go to your electrorefining plant. So you have a whole loop of conversions and transformers before you go from the DC power in your PV plant to the DC power in the copper electrorefining plant. So you wonder, maybe is it possible to do something like this, right? To go directly from the PV plant with the DC-DC converter to the electrorefining plant. And we did some R&D on this. We're still doing, actually, we are not now at stages in which we are improving our technology. So we did some DC-DC converters to go directly from DC power, from low voltage DC power from the PV plant to low voltage of the DC power in the electrorefining plant. Here, one of the students I worked with that got an award somewhere because of her conference paper. We have not, since then, moved to more larger scale prototypes, and we're now looking really into doing a prototyping industry with this technology. So another thing that we have been looking into is partial power converters for the DC-DC stage of photovoltaic energy systems. This is to increase the efficiency. So central inverters don't have a DC-DC stage, but we are currently moving. Most of the PV plants now are being installed with string and multi-string inverters that have a two-stage conversion system that do have this DC-DC converter over here. So, and this improves a lot of things related to the power plant, particularly the energy yield, because you have a better MPPT of the PV system. The problem is if you add this converter, you have additional power converter losses. So we're trying to tackle this down with this partial power concept, converter concept, in which you have a very much smaller DC-DC converter that only takes a part of this power of the PV system to process it, and you still achieve MPPT, but with a smaller power converter. This is a concept that has been used in other applications before. We have been doing some research on applying this to PV systems, and here you can see two power converters that we have developed. One for smaller scale applications, this is for micro inverters, this one is for string inverters, and you achieve really high efficiencies. With this one, we achieved a 99.8 peak efficiency, and with this one, 99.57% peak efficiency measured with very high precision instruments. In terms of the problem in transportation, like I mentioned, the biggest one is for electric vehicles is the infrastructure, the charging infrastructure. So as you can see here, we have AC slow charge, AC fast and medium fast charging, and then DC fast charging, which is the big charging stations. And we are tackling this one, which is the one that really shortens the charging time. And again, we use the same technology I showed you before, the partial power converter in the DC-DC stage, which is the one doing the regulation of the battery. So here, instead of doing an MPPT for the PV side, what we're doing is following this special current and voltage control system to actually perform the battery charging as it should be. And again, you don't have to process all the power in the DC-DC stage. You can do just a fraction of it. We did not achieve the same level of partiality that we achieved in PV, because in PV there was less voltage fluctuation, so we could get away with a 10% of partiality. So just a converter which is 10% of the total power capability of the system. Here we achieved only a 30% partiality, because the batteries, when they are discharged up to when they are charged, they have a larger range of voltage. So this is one of the converters that we proposed for the solution, and here you can see the measurement, the efficiency measurement. Of course, it's a little bit lower than what we got for PV, because we have a different, a wider voltage gap, of wider voltage difference. Here you can see the prototype, the picture of the prototype where the measurement was taken. It's a 5 kilowatt converter, and it could charge up to 15 kilowatt because of 1/3 power rating. We are now scaling this up. Here you can see a 50 kilowatt prototype that could make a real charge of 150 kilowatt, also with the same partial power concept. The student worked on this topic. He won this ABB Chile Award for Innovation in Energy Efficiency last year. So coming back to the plane, right? Remember I talked to you about the plane before. So what can be done? This is not something that we are doing in our group. And I'm getting to the end of presentation, so this is kind of like a last concluding remark or example. Well, the people are pushing other ideas that are a little bit outside of the box. So probably you've heard about Hyperloop. This is this low pressure tube in which you have a levitation magnetic train inside. So it's not really a train because you go inside this tube that has no air friction. And because of this, you reduce quite a bit of the losses because the losses are proportional to the square of the speed, which is what you get when you have friction with the wind, with the air, which is not this case. So here you can achieve way faster speeds, even more than current airplanes. And you of course have the capital expenses of this tube that you wouldn't have with an airplane, but it pays back because of this efficiency in operation. There are a few companies already looking into this concept, like Virgin Hyperloop One, and there are already some commercial projects being financed and being planned, not yet fully developed, of course, but they are really in the making. One of them is actually this one here between Mumbai and Pune. This is by Hyperloop One, and it's going to be joining Mumbai to Pune with a stop in the Navi Mumbai International Airport, and it would make the trip only in 25 minutes. That actually currently is 2.5 hours by car or 3 hours by train. So this is a very fast point-to-point transportation system that doesn't need really to be massive. So you don't. One of the nice things here that it does not need large-scale economies like planes and trains, in which you have to put more than 200 people in them to make them cost-effective. Here you can have smaller pods because you don't have this problem of the to really scale up the economies, because the operation is quite cheaper. So final conclusions. Energy transition technologies must be sustainable, so they need to be economically feasible, socially acceptable, and environmentally friendly. So if it doesn't comply with these three concepts, it is not something sustainable. So for example, the thing I just mentioned, the case of the Hyperloop, it seems to be economically feasible. People, I think, will accept this. There are some speculations on whether people that may get a little bit claustrophobic and stuff like that, but they are actually working on the user experience, and it's actually environmental friendly because it uses electrical energy that can come from renewable energy. So that would be something that looks like a good project. So this is something that if you are looking into some solutions, please have into consideration that it has to comply with these three criteria. Also, that the solutions need to tackle, in my opinion, you should focus on the things that are large-scale issues. So I know it's very interesting sometimes to look regional aspects, like where you live, some solutions that are based on the territory, or that cater a small niche. But actually, I believe that if you want to make a real impact, you should be looking at large-scale topics and high impact at the global level. Right? This is not something that's going to be solved by having a clean transportation system in New Zealand. It has to be also in China, in Russia, India, and the whole rest of the world. So global level and large scale solutions are the ones that you should look into. Also, industrial electronics and all the components of industrial electronics, power electronics, the computational systems, communications, and robotics, everything's underneath industrial electronics, are enabling technologies in terms of getting there to energy transition solutions. So you are definitely in a field in which you can make a difference. So take advantage of that. You already made the decisions to study electrical and electronic engineering. And like I mentioned, this is an energy problem. So this is where the solutions might be. Even you could actually solve stuff in the other area of greenhouse gas emissions, like I mentioned, which are related to the uses of the land or agriculture. Even in those things, you could lower the carbon footprint by using solutions made with based on industrial electronics. So the message you have to take away with this is that, of course, this is a difficult issue. It's a challenge, but challenges and problems are like little golden nuggets for engineers. So there's plenty of room for research, development, and innovation. So you should be happy on that side of this crisis, right? So crisis, there's a saying that is, don't spoil never a good crisis, because there are a lot of opportunities that can come around, can come about that. So you can be part of the change. And that's a little bit the message that I have for you. So I hope you enjoyed the presentation. You have my email over here. So if you have any questions, you please just send them to me, to my email. Say that you saw this webinar in the Young Professional Forum of the IEEE conference, and I will be more than happy to answer them. So yeah, that's it. Thank you very much.